Now we get to transition a little bit to think more about assessing management impacts for water. So Dr. Dianna Bagnall will be with us now to share that. And she is a research soil scientist with the Soil Health Institute. Her research includes developing functions that show the soil carbon on plant available water, selection of the most effective soil health indicators for the North American continent, on-farm soil health assessments, qualitative analysis of farmer interviews, development of novel soil structure scanning methodology, and both measurement and modeling for preferential water flow in shrink well soils. So very excited to get out of the way and let Dr. Bagnall share all of this amazing information. But again, please put your Q&A in the chat and we will be answering those questions.
Thank you very much, Dr. Odom. And sound all right? Everything looks good? I'll take that as a yes. Well, thanks, Dr. Odom, for that introduction, and thanks, Dan, for that excellent presentation. As we shift to looking more at the water cycle from the carbon cycle, I wanted to start by just sharing some resources. There are many manuscripts that are going to go into the things we're going to talk about today. At first, we're going to be talking about aggregate stability. If you got to hear the farmer panel yesterday, you got to hear about soil structure and how important that is to the water dynamics for adopting soil health management practices. So we'll talk a little bit about that manuscript, and here's the title. Hopefully it will be published soon in Geoderma. The next two manuscripts are available now, and they're open source at the Soil Science Society of America Journal. So in that second manuscript, we're going to talk a little bit today about some other indicators aside from aggregate stability, looking at how much water our soils can hold and provide to crops and how that responds to soil health management. Also looking at things like bulk density, a measure of how compacted our soils are or whether they have good porosity. And lastly, maybe the most exciting piece for me is to be able to tie together some of the pieces that Dan was just describing in talking about the carbon cycle and talking about the water cycle, relating carbon to plant available water. And if you'd prefer to read something a little shorter than a peer-reviewed publication, this link at the bottom has all of the outcomes from the NAPSHM project, the North American project to evaluate soil health measurements that we're discussing today, including some short interpretive summaries of several of the papers. So let's go ahead and dive in. First, I want to talk about aggregate stability. And we looked at 4 different indicators of aggregate stability in the North American project to evaluate soil health measurements. So at each of the 124 different sites, we looked at these values. One was the water stable aggregate percentage, and it's underscored CASH there for the Cornell soil health assessment. So in that methodology, we're using a Cornell rainfall infiltrometer or simulator to apply water to the aggregates and then seeing what proportion of those aggregates are stable against that simulated rainfall. A similar but slightly different test, water stable aggregates underscore or lowercase ARS there, is looking at wet sieved water stable aggregates. So in that case, we're looking at aggregate stability and seeing what proportion of our aggregates fall out and are unstable when they're exposed to a solution. Kind of a different measurement here, stability 10 or STAB 10 as we've abbreviated it, is where we're taking a smartphone and capturing an image of an aggregate both before and then after a 10-minute immersion in water. And so if the aggregate is not very stable and our structure isn't so good, we're going to see a lot of slaking, and that aggregate's going to be much bigger at the 10-minute time mark. If we have very stable aggregates, we'll have a smaller difference in the 2 images. If you're familiar with the Slake smartphone app, this is a really similar methodology. And lastly, we're going to look at mean weight diameter, abbreviated MWD. And for mean weight diameter, what we're doing is looking at aggregate stability across several different size fractions and then kind of taking an average of those different sizes to arrive at our mean weight. Now, as Dan laid out so well in his presentation and as Wayne discussed, we have a range of inherent properties sampled in the North American project to evaluate soil health measurements. All of these aggregate stability measures were influenced by inherent properties, things like the soil texture and the climate, looking at things like the amount of rainfall that they received. And all of them are moderately correlated with each other, which is another theme you heard from the last talk on carbon, that there are a lot of indicators that are useful and that are giving us, in general, similar results. But let's look now a little bit more specifically at what the outcomes were in terms of the response to management for these 4 aggregate stability measures. So in this graphic, we have on the x-axis the change in response to these different practices. This is the log response ratio analysis, and we've transformed it to percent change. So a value of 10 on each of the x-axis for these panels represents a 10% increase in the indicator in response to a particular management practice. So if we look up in the top left-hand panel, here we're looking at that practice of residue retention. So for example, the gold dot, water stable aggregates cache, is somewhere around the 20 mark. And so that means that there was a 20% increase in aggregate stability with the water stable aggregates cache when we retain our residue. And then as well, we have those gold bars, and those bars are the 95% confidence interval. Since they don't overlap the vertical 0 line in this case, we find that it's a statistically significant change. And so it's a good thing to see that this principle of soil health, which is to retain our residue and armor our soils, is showing an increase in aggregate stability for 3 of these 4 indicators. Those are water stable aggregates cache, STAB 10. I know STAB 10 looks like it's right on the line, but it is an increase, and also mean weight diameter. But what we're going to see as we move to the next panel for organic nutrients is that we don't see the same behavior of all the indicators for different practices. So for example, in organic nutrients on the top right there, we see no change for water stable aggregates cache or STAB 10, but we do see a change for the other 2, water stable aggregates ARS and mean weight diameter. Looking at cover crops, that trend we just saw for organic nutrients is reversed. So we see 2 of the 4, those top 2 being responsive to cover crops. I will note that we had fewer cover crop treatments than just about any of the other management practices. And so that is one possible reason that we have a little bit lower responsiveness to the cover crop practice. But I think it's really informative as we move over to the bottom right to see that every single one of these indicators responded to reducing tillage. That's really logical when we start thinking about building our soil structure. If we are tilling our soil frequently and it's a lot of disturbance, it's going to be really difficult to build soil structure and stable aggregates if we keep going through and destroying them. So I know this graph is a lot to take in. We're going to summarize it here with a few bullet points. But one thing I'll note before we leave is that all of these 4 indicators, except water stable aggregates ARS, were sensitive to 3 of the management practices. Water stable aggregates ARS was only sensitive to 2 of these 4. So to summarize what we learned about aggregate stability, broadly speaking, these indicators are sensitive to tillage, to cover crops, organic amendments, and residue, but they weren't sensitive to crop count or rotation. Those graphics are omitted from this presentation for brevity, but they are shown in the manuscripts at the links that I provided if you're interested in taking a look at those data. There's not one aggregate stability indicator that's the most sensitive across all of the management practices that we looked at in the North American project to evaluate soil health measurements. But we did see that water stable aggregates ARS was our least responsive indicator. So just as Dan was speaking about, needing to winnow down a little bit and look at what should we recommend to scale soil health, which is really the theme of this session, but even the entire conference. And so we've selected here STAB 10 because of its affordability. It's probably on the range of $5 to $10 per sample, which is about half of the cost of the next lowest cost that was sensitive to management practices. So we're going to kind of put a pin on that in terms of the recommendation and jump over to some of those other management or other indicators that I was mentioning. So briefly, we're going to be looking at bulk density, abbreviated DB. So we'd like to see that our management practices give us lower bulk density, indicating less compaction, and that our soils have more pore space. We're going to be looking at this measurement of volumetric water content at permanent wilting point. This is the lower limit at which soils can hold water and still be able to provide it to plants. So it's really important in thinking about drought resilience. And similarly, the upper limit at which soils can hold water and still provide it to plants is called field capacity. And so we measured field capacity in two different methods. One, which is a more typical method, is to take soil that has been ground, and so the structure has been lost, and then we repack it and measure our field capacity on that. But a second, less common methodology that we used here for comparison was to take intact soil cores, so we don't disturb the structure, and then we assess field capacity. And I want to highlight how important permanent wilting point and field capacity are when taken together, because if we have a larger difference between them, we're able to have more plant available water, and that's critical for our drought resilience and something that's a major goal of soil health management practices. We also looked at saturated hydraulic conductivity at each of the sites, which is a steady state infiltration measurement that we can look at. So I'm going to launch into another graph now and talk a little bit about these results. This is the same interpretation as the last graphic that we were talking about. So we once again have our indicators arranged on our y-axis, and on our x-axis, we have the percent change for the response to management for each of these different practices. And the practices are the same and in the same order. So we have residue retention, organic nutrients, cover crops, and decreased tillage. So this is a little bit more repeatable, or there's a little bit more commonality than we saw in aggregate stability. So starting in the top left, I wanted to call your attention to this bulk density with this little blue circle. So our bulk density was significantly decreased by retaining our residue, by armoring our soil. That's good news. It means we're likely to have less problems with compaction and that we have more pore space. When we drop down one and look at that theta PWP for permanent wilting point, we see no change statistically in response to management. And we also don't see any change for theta field capacity repacked. So when we use those repacked samples where our soil structure was disturbed, we're not seeing any difference in the lower limit or the upper limit for our plant available water, meaning that that plant available water wasn't responding to residue retention. But the really good news is that when we use an alternative method, this field capacity intact, where we're in keeping our soil structure, when we're measuring our upper limit of available water, we do see a significant change. And this means that because our field capacity has gone up, our plant available water will also go up. Now, if we look at that last dot, it's for KS, or saturated hydraulic conductivity, and you'll notice just the massive bars around this. The 95% confidence intervals for all the management practices for saturated hydraulic conductivity are huge. And if you have experience with infiltration and KSAT in the field, you know that it's extremely spatially variable, and it's time consuming and somewhat difficult to measure. And so the story here is that while this is a really useful measurement and valuable for research purposes, the variability was simply too high for us to be able to recommend this as a measure to scale soil health across the continent and potentially beyond. If we move over to the right top panel for organic nutrients, we're going to see the exact same pattern. Organic nutrients is improving our bulk density by making it lower. It's improving our field capacity intact by making it higher and increasing the amount of plant available water, and the other indicators weren't responsive. Now, I mentioned in aggregate stability that we had a relatively low number of cover crop treatments, and this is potentially one reason that we see no response on that bottom left panel of any of the indicators to cover crops. Another piece to remind you of is that we're looking at these in isolation largely. So this is the impact of cover crops alone and doesn't really tell us about the other benefits that cover crops might have while we're using other soil health management practices. Moving to the bottom right, on bulk density and field capacity for decreased tillage, we once again see lower bulk density, which is good, and higher field capacity. So I'm going to summarize this with a few bullets as well. Across these sites, we saw that the indicators bulk density and field capacity, when we measure on intact cores, were responding to our management changes in general. But when we use those repacked cores, either for permanent wilting point or for plant or for field capacity, we don't see a change. Now, field capacity for intact cores is very responsive, and it's a very direct, meaningful indicator because it's telling us about our drought resilience in these soils. But I've fallen short of recommending it here because I want to take a moment and move over to that last publication that I mentioned when we were starting off. So to talk about this, I want to talk a little bit about the idea of a function or an equation that we call a pedotransfer function, by which we can take information that's quite easy to access or that we might already have on hand and predict something that's harder to measure, but that's really important to us. And so a good example of this is the common use of things like the clay content, sand content, and soil organic carbon of our soils to be able to predict plant available water. However, there are many pedotransfer functions for plant available water, and they all show no or very small changes when we go to soil health management systems that increase our soil organic carbon and increase, and so we don't see increases in plant available water. However, when we used the North American project to evaluate soil health, we took those intact cores and we fit a new function to predict plant available water. We were able to generate the graphic that I've got here at right, and that's in, you can view more at the link that's down below. So on the y-axis here, we have plant available water in percent, and we're controlling for clay content and sand content here. And so we've got clay content on the bottom axis, just to show you that indeed, the plant available water is responsive to clay content, but the real take home is here with those different line levels. When we go from 1% to 2 to 3 to 4% soil organic carbon, we see some pretty substantial increases in plant available water. And this is a little more than twice the impact that past pedotransfer functions have shown. So this is really important because it allows us to link this really critical measurement of drought resilience in terms of plant available water to differences in our management that are increasing and that we're representing through changes in soil organic carbon. So with that, we're going to go ahead and talk a little bit here about what we're recommending for the water cycle. When we look at these indicators and we took a look at all the data, an affordable and sensitive indicator to management is this wet aggregate stability using image recognition. That's that STAB 10 that we looked at in our graphs. And then if we need to generate some more information here, we have the option of using sand, clay, and soil organic carbon to predict plant available water, which is important for drought resilience. And I want to just close here with this image because I think this is great. These are farmers in their field. They're looking at aggregate stability. They're looking at their soil structure, and they're looking at the difference that their soil health management systems are making. So to me, this lines up so much with the measurements that we're recommending and what our farmers are looking for when they go out to see if their management systems make a difference. There are many people to thank. Our present and former SHI staff associated with NAPSHM, our partnering scientists, and of course, the generous support of the Samuel Roberts Noble Foundation, General Mills, and the Foundation for Food and Agriculture Research.
Thank you so much for that. We do have a number of questions in the chat, but I think we can take one if we can answer it quickly. And that was, there was a question from an attendee that said, are there common amendments that contribute to aggregate stability, humic acids, biochar, or others?
Yeah, that's a good question. It was not something that we specifically looked at in the identity of those organic amendments, so I can't speak to that in terms of this data.
Okay, perfect. And there are some other questions for you in the chat. I see Dan's been doing a great job and Christine have been covering those. So if you can go in and if there are any others that you could answer, I'd really appreciate it. Thank you so much.